let's get started. And today we're going to talk about a couple different concepts. I'm going to try and get through hierarchical modeling, and then we will continue hopefully with a little bit about ray tracing, but that may not happen today. It depends on how much I talk. But hierarchical modeling. So the objective of the lecture is basically take a look at the concept and how it applies towards computer graphics. It applies towards OpenGL as well as VRML and other graphic packages. And the concept is that the objects are hierarchically placed so that they work with each other and they form the world, or they form the object. So a humanoid, and actually if you think about the concept, it's like real life. A humanoid, you're a human. You know, if you put you on a computer and you had to resemble you're going to have fingers, you're going to have hands, and your arms and legs, and these are all different sub-objects that make up the big picture. So in computer graphics, what we try to do is create a hierarchy of objects. So we build a tree structure that models the humanoid figure. And I'm going to use a humanoid as an example in this lecture. And we're going to examine the various different traversal strategies to traverse through the pieces of the objects that are connected together, and then build a generalized tree model structure that is independent of any particular model. It's just a hierarchy that's representing the figure or the shape. So here's our humanoid. And we started in the middle, actually, with the torso, which is kind of interesting because if I were to model a humanoid out, I could start with the head and go to the neck, and then go with the torso, and then go with the arms, and go with the fingers and the hands, and go with the waist, go with the legs, the upper leg, the lower leg, the toes, and go like a top-down approach. Or I can start it in the center, and I can go outward. So from the center, from the torso, we've got the head, we've got the left upper arm, the right upper arm, the left upper leg, the right upper leg, that are all connected to the torso as a center point. So don't think of this hierarchy as a top-down or a bottom-up hierarchy. It's more of a representation of how the pieces fit together in terms of the components. And so you can see in VRML, actually, even when you created your spaceship, hopefully you've done that assignment, which was the first one. And I think, believe it or not, I think one of the assignments actually has you create a humanoid or something of that nature. And think about the hierarchy of the components and how you're going to work that together. And just as kind of a preview, today we're working with the hierarchical structure and the concept of ray tracing. Next week we're going to work with animation. I'm making a little note here because I need to make sure I cover animation in computer graphics so that we can kind of conclude out a lot of these major topics. So building the model. So you can build a simple implementation using quadrics, cylinders, squares, rectangles, anything you can possibly come up with. And you can have access parts through functions. And so if you're using a programming language, and this is actually in a C-like kind of syntax, or Objective-C actually, but what we're looking at is a torso function and upper arm function. These are just examples. In fact, you can do this with object components in VRML as well. You can create, this is the torso, and the torso has in this shape and that shape and this shape, and this is the rotation, and this is how we're going to orient it. And then we have a matrix that describes the position of each one of the nodes with respect to its parent node. So the positioning starts so we can move an arm around, rotate a head around the axis. So the M standing for the position, M to the 11A positions that are left, let's say left lower leg with respect to the left upper arm. So we can put things in correlation with each other, and then we can create how the hierarchy can just kind of traverse through the model and rotate so that everything moves together, as an example. So here's a tree with the matrix that are assigned to it. So the M would be the matrix for the head. And by the matrix, we're referring to the coordinate systems. So this is the points in the XYZ plane that are going to coordinate to where the head is positioned in terms of the relationship with the origin or relationship with the view projection, depending upon how we're going to represent it. So the torso here has got a different metrics for, let's say, the left upper arm. And the indication here is just M for the matrix, and then left upper arm, right upper arm, and just kind of the abbreviations of all of these different things. Because we're not going to look at this. Programmatically, we're going to look at the coordinate system, and we're going to look at the points that are in the matrix for each one of the different coordinate systems. So, and the matrices that are associated with it. So it's displaying and traversal. So when we go through a tree, which kind of loosely resembles a tree, but it's really traversing through sets of coordinate systems, we're going to make it to certain points, and we're going to be represented by certain positions. So the position of the figure is determined by the 11 joint angles in this particular case, 2 for the head, 1 for each one of the other parts, and displays the tree requires a graph traversal. So this is kind of like where the graph of the nodes comes into place. So you visit each node once, you display the function at each one of the nodes that describes the part associated with the node, and then applying the correct transformation matrix for the position and the orientation for each one of the node pieces, which gives us our overall functionality and our overall node correlations. So this is where the transformation matrices comes into place. I always mispronounce that word for some reason. So there's 10 different relevant matrices that are associated with this one humanoid picture. So we have M positions and orients that entire figure through the torso, which is the root node. So if we call the root node the torso, when we move out, we can traverse through all of the different positions by traversing the tree. So the M positions are the head with respect to the torso. And then we have all of these other ones, what are positions of the arms and the legs with respect to the torso. And then these other positions are the lower parts of the limbs that are respected to the torso. And just to revisit the big picture, this is what we're looking at. So we have all of these different matrices that are associated with the positions. So you could possibly see if we develop a relationship between all of the pieces, we create the hierarchy. And when we create the hierarchy, we apply something to one piece of the hierarchy, and everything else just flows with it. So we can turn this humanoid around, make him go to the left, make him go to the right, move an upper arm or move a lower arm or a foot or a finger or something. We have no fingers in here, but and then rotate everything else in the same relationship using the same coordinate system that's associated with the individual component, and rotate everything by 5 or -5 or something. And then we end up with the ability of creating the relationships between the different nodes. Think of these as nodes in a tree, and you move part of the tree and the whole tree moves with it. You know, it's kind of like a regular old tree that we see. You know, take off a branch and you have everything with the branch that's associated with it, that's in orientation to it. So in terms of the programming aspect of it, we can represent it with a couple of different data structures. What we normally come up with is this thing called a stack. So a stack-based traversal. So a stack. I'm going to assume you guys don't have a programming background, so I'm going to kind of describe what a stack versus a queue is, because then you can rotate and animate through using this data structure. So a stack is a data structure just like a stack of plates, where the first in is the last out. So if you're unloading a dishwasher as an example, or you're taking something out of a box and it's a bunch of plates, normally when you open up the cabinet you put the first plate down, and then you put the second plate on top of the first plate, and then the third plate goes on top of the second plate, and the fourth plate goes on top of the third plate. And you're putting them in, and when you take them off, you don't normally lift up all the plates and pull the one on the bottom. You normally pull the one off the top. So the first one that goes into the stack is the last one that comes out of the stack. And they have this thing called pop and push, which are methods that you run to pop takes something off of the stack, and it's usually the last element that was put in. And push puts a new plate onto the stack, adds a new item in there. That's a stack versus a queue. If we used a stack at the bank line, we'd have a lot of yelling and screaming customers. So instead, the stack is a first in is the last one out. So a queue is the opposite. It's the last one in is the first one out. Excuse me, the first one in is the first one out, is what I meant to say. So in a queue, you line them up. So you take those plates and let's say put them on their sides and put them in through like a rotation device of some sort. So the first one you put in is probably going to be the first one hopefully you take out, which is a queue, which is a line at the grocery store, a line at the bank, or something of that nature, where we, you know, it's fair because the first person who arrived is the first person who's going to get waited on. However, it doesn't work quite well for certain solutions, like the example of the plates. if we tried to, if you pulled the plates out fairly, then what ends up happening is you're going to break all the plates. Because if you got 50 plates lined up and you have to get the one on the bottom, not going to work. In fact, when you pick up all the plates, you're probably going to drop them. So for that solution to that problem, a stack makes more sense. So actually, that's not too bad. You now know the difference if you take a data structures course between a stack and a queue, hopefully, which you'll get if you take a programming course or data. I believe the DA students, there's a programming for math, math and programming, or programming for digital arts or something, or for arts. It's on the schedule, I believe. You may not have seen the schedule yet, but I think it's coming up, actually. So you'll learn more about matrices math, adding two matrices together, as used in graphics, which I didn't do in this class. And you'll also learn about data structures and programming syntax and stuff like that. I believe Cornell, Dr. Pokorny, I believe it might be teaching that course. So you'll look forward to meeting with him, hopefully. All right, so the stack-based traversal, now that we know what a stack base is, we're going to traverse it using a stack. So we're going to line up the humanoid. And the first one in is really going to be the last one we're going to work at. So we're doing it in the reverse order, which is kind of interesting. If we think about rotation and movement, is it really the outermost piece that moves first? So, and then everything else moves with it. Now, if there's an example of a humanoid, just pretend like I'm a humanoid. I have a hand here, and the hand's down here. I'm going to move the hand up this way. Everything else has got to move in association with the hand. So if I start this way and load everything in, this is going to be the last item that's going to move. My forearm, this part here is going to be the last. This is going to be next, and this is going to be next. So I go to the bottom of the stack, or the last item in the stack, which are the fingers or the palm, let's say, for example. Let's say I don't have any fingers, I just have a palm. I'm going to rotate it, and I'm going to move it up here, so the coordinate system in the matrices for this is changed, and then we translate it, which is called the translation, which is the traversal, because we're going to go through the tree of objects, and we're going to move, because we can't just put this up and then have everything else just still down. It doesn't work in the human world. It does work in computer graphics, so you see it all the time. Like the hand goes up, but what happened to the arm? Where's the arm to follow it? So if you treat it like a tree and you coordinate it so that they're all associated, then you can rotate the rest of the objects that are associated with the palm so it all moves up together. And then you have realism in computer graphics, and you have the proper relationship between the nodes. So that's what we're talking about. So you set the model view matrix to M and draw the torso. And then you set the model view matrix to MMH and draw the head. Until you draw the torso, how do you know where the head's going to be? You could start with the head if that was the base root. So the order in which you're going to draw this thing, if you're working with the torso as the root of the tree, you're going to put the torso in first. Once you find the starting position, then you're going to go, okay, head in relationship to torso, arms in relationship to torso. And then you're going to either go down the arms or you're going to go down the legs first, depending upon which order you want to do this in. And this is up to the programmer, or up to the person who's implementing this. So for the left upper arm might be needed for the next one, the right upper arm might be needed. So rather than recomputing everything from scratch or using an inverse matrix, use the matrix stack to store the matrices and the others. As the tree is traversed, then you know what order you're supposed to put things in. So the stack-based traversal is used to determine the order of the painting or the drawing. So we have this figure method, and we're just going to use OpenGL as an example in this particular case. The method calls are a little bit different in VRML, but let's just use this. So we have a GL push matrix, which says, save the present model view matrix, and then run the torso. For the torso, we're going to update the model view with the head. So then we're going to do the head method. Then we're going to do the upper arm method. And what you get out of here is not necessarily an understanding of what the code is doing, because there's no method implementation here. It's just the method names. And the method names are basically going to be broken out into the functions to draw the head, draw the legs, draw the arms, and draw the rest of the code, essentially. So in the analysis of this, the code describes a tree, so a specific tree in a particular traversal strategy might have different ones with different people or with different humanoids. It's made up. So a more general approach is needed to actually put this into place. So animation software actually comes up with these general approaches. Like, it's already built into the VRML, so we don't actually have to do this level of work. In OpenGL systems, we might have to actually, depending upon what API we're using. So an important point, the sample code does not include state changes, such as changes in colors, which is kind of interesting. So we've been talking about orientation in terms of the matrix of where the object is appearing in the XYZ plane. But what if my arm, in fact it would be natural, if my hand, if I bang my hand a few times, it might actually turn red. If I bang it on the table, let's say, not a good thing to do, but I'm noticing it's a bit red, probably just from being in my pocket, maybe from the cold air. But is the arm red? Not really. So we don't get too much realism. If we paint color and it doesn't oh look, the arms, the feet turn blue, and look at, there's a discrete line where the feet ends and the leg starts, but only the feet or only the toes are blue or something, then it doesn't look as real. So we can apply the same concept as a general model to color, to lighting, to shade, to other things that we've seen so far. So we also want to use a GL push attribute and a GL pop attribute to protect against unexpected state changes that are affected later parts of the code. So, oh, we changed the color. Maybe we should fade the color. So, in fact, when your face turns red, the whole thing doesn't normally turn red. It's only parts of it will. Well, that's because you're applying an attribute maybe that's not going to everything. It's only going to your nose, or it's only going to your cheeks or something, or your eyes or something like that. And the entire model is not being transposed to reflect the color changes. Otherwise, it would be like, how many people have you looked at and their entire body is red? Not very realistic. You just applied it to everything. Now you're red. Oh, look at that. Your hands are red. Now you're blue. Oh. So general tree data structure, you need a data structure to represent the tree and an algorithm to traverse the tree. So use a left child, right sibling structure to paint from left to right, from top to down. You can use linked lists if you're going to implement this from a programming perspective. Each node in the data structure could be 2 pointers, 1 pointer to the next node. If you're doing this by hand, a linked list makes a lot of sense actually. So more so than an array, but you could possibly use an array as well. Or you can have the left, which is going to be the next node, and the right, which is going to be the linked node of the child node. So if you're not familiar with linked list, don't worry about it. You'll learn that in data structures course, or a programming course as well. So here's the root, and here's the linked list. And a linked list is nothing more than memory locations and pointers to memory locations, and that's how you're creating the list. So you're really taking this tree structure and you're putting it and representing it in the form of a list. And you're taking the list and you're going to the next item, next item, next item, next item in this particular example, so that you can go from point A to point B and C and visit all of the nodes, and so that you're painting everything. So you're basically traversing, which is the word traversing is sort of referring to that. So in the tree node structure, each node you need to store the pointer to the sibling of the node that follows it, which are these black dots actually. They're pointers to each one of the nodes that it's going to be hopefully going to. And the pointer to the child, and a pointer to the function that draws the object represented by the node. Because the object's going to do something, or the node is representing an object, so something's going to draw the object, and then you're going to go next to the next object, draw that object, and go next to the next object. So the homogeneous coordinates matrix that to multiply on the right of the current model view matrix, so you can get the pieces to translate, and represents changes going on from the parent from parent to node, parent to next node. So an OpenGL, the matrix is a one-dimensional array storing columns by, but matrices by columns in a one-dimensional array. So here's some examples. C code that defines a tree node. So we have a structure for the tree node, and this is basic C programming. You may not be familiar with it, something that you'll need to learn. So if you're going to Okay, so here's the thing. So for the most part, you can get by using the VRML for concepts to learn graphics. But eventually, if you're going to get into computer graphic programming, you'll have to apply it towards a language. C, C++ are the traditional languages that are being used for this, and it's OpenGL packages or libraries that are being programmed. And so you would create a linked list, and then the linked list would have the nodes in them, and the nodes would be the pointers, and that's how you would create the connection between them. If you use a higher level API, you're dragging and dropping, and connecting graphically without writing any source code, which is sort of like what you can do with VRML actually. But VRML is sort of no data structures, no source code. You're just creating these objects, and you're putting the objects together. And it's your imagination and your programming that's going to connect them so that they look like a humanoid, or that they look, which is not as sophisticated as writing the source code for it. But at certain levels, you may not necessarily need that. In fact, VRML is a great language being used currently for web graphics, web modeling. And it's nice because it's, easier to use, more friendly, and a lot more sophisticated, essentially. It gives you virtual reality kind of components as well that go along with that. So, all right, so going back to the programming part of it, because most people who look at this go, programming? When am I ever going to do that? Well, if you open up OpenGL and you want to write some code that's going to do some graphic development with OpenGL, you're probably going to have to learn C eventually. This is an array. This is a function call. Function call is sending. It's not returning anything, so it's void. And we're sending a pointer to it. The pointer is going to be the sibling and the child nodes. So there's going to be more nodes of the tree node structure variety. So we can define the torso node. And the torso node is going to be this coordinate of sets. So it's going to be, looks like it's going to be a rectangle with the 4 coordinates here. And we're going to create this rotating function that's going to work with it. It's going to use the coordinate system. I'm not going to go through the code because it's going to be Greek to you unless you have a familiarity with the C programming language, which I'm going to assume you don't. So some notes to take in terms of what's going on with this code. The position of the figure is determined by the 11 joint angles that are stored in the theta 11. The theta 11 is nothing more than it's going to be nothing more than an array, and the array is going to store each one of the 11 joint positions. We keep track of the vertices or the joints because then we know which position the next piece is going to go to. So we have the nodes and we have a list of vertices, and then we refer to them to know what node comes next in the hierarchy, and we put the pieces together, keeping track of it. So we can animate it by changing the angles and redisplaying it. So changing the angles of the vertices would actually do that for us. In this particular point, we're calling them, the vertices are called the joint angles. So we can form the required matrix using the GL rotate or GL translate, which is equivalent to rotate and translate in VRML. So it's a built-in functionality that's going to provide the rotation for us. So more efficient than software, so because the matrix is going to be, depends on what software you're going to use for it, but this is generally a more efficient way if you hard code it in C or C++. And because the matrix is formed in a model view matrix, we might want to first push the original model view matrix on the matrix stack and then use a hierarchy for the actual world that we're going to put together. So this is an example of a humanoid. We might have other humanoids, other animals, or something else in the scene. So we can actually apply the same concept to all of the components. We can also come out with a preorder traversal, so when the guy moves, it moves with the foot first, and then the foot gets planted and the body moves with the rest of it. Or he can move the hips first and then the leg last. So just think about how bodies move. Then we can kind of pre-order the traversal so we know how we're supposed to move to create more realism, better animations, I should say. So some notes on the concept of preorder traversal. You must save the model view matrix before multiplying it to the next node matrix, which means you have an existing state that you need to save, and you have a transfer to this state that you also need to capture because you need to go from point A to point B and capture the distance between the two and be able to calculate that to translate it out, which is kind of interesting because if you think about how humans and robots move, if your humanoid has 2 or 3 parts to the leg, the whole leg doesn't move together. All parts of it don't go simultaneously together. Usually there's a foot component that goes first. Like, you know, just think about when we walk. The foot's going to get planted and the rest of it is moving with it. So we have to take that, and that's what's referred to as the preorder traversal, that logic of being able to move the entire leg, starting with the foot going up to the hip or the arm. That's a preorder. We already know the order that that's going to occur, and every time you move the hand up, everything else is going to occur with it. So if you hard code that and set that, we only move this way. I can't move, I guess I could move it this way. But that's not in my preorder programming. I'm not going to move my arm up like this. Actually, it's interesting when people just change the order around and then it looks different. So that would be called breakdancing, I guess. So let's see. We update the metrics and apply it to the children nodes, but not to sibling nodes, which contains their own matrix themselves. So every one of the objects has its own matrix that can be transformed and translated. So the traversal program applies to any left child or right sibling tree. So the particular tree is encoded in the definition of the individual nodes, and the order of the traversal matters because of the positive state changes in the functions. So we have dynamic trees. So we can use, if we use pointers, the structure can be dynamic. So it can change, and we can keep adding things to it. So if we can grow a new limb or something, we can essentially accommodate that change. I don't know how many humanoids or how many humans grow new limbs, but we could if we had an object that grew something new or something, which makes it dynamic. So the definition of the nodes in the traversal are essentially the same as before, but we can add and delete nodes during the execution. So we could cut something off or add something new. We can morph. The dynamic trees would create a morphing effect, by the way, so we could change somebody into somebody else or transform the image with using its hierarchy as it's translating and moving throughout the scene. So graphic objects and scene graphs. So the next topic works with the concept of creating the world from the hierarchies of the objects. So we're looking at the graphical objects themselves, generalizing the notion of the objects to include light, camera, and attributes, and introduction of scene graphics. So this is putting the pieces together with color, with lighting, shading, the view perspectives, the objects, the hierarchies of the objects. So this is really the big picture in terms of what it is we're composing with computer graphics. So the limitations of immediate mode graphics, which is kind of interesting. So when geometric object is defined in an application, upon execution of the code, the object is passed through the pipeline. It then disappears from the graphical system, and to redraw the object, either the modifier or the same code, the code must be re-executed. So what we get is not like a picture that appears automatically. So in computer graphics, that's not, you know, saved in terms of images, but actually generated. So you're generating the graphic. You're going through the pipeline, which is one of the limitations. So you want to maximize the speed of that pipeline so that the entire image gets presented. And then we can do things like double buffering and stuff. So we can keep a copy of that image just in case we want to paint it again. We don't have to go back through the pipeline. We can go back and look at a saved copy of it and bring it forward. So things like buffering and double buffering, triple buffering helps us create more realism and gets rid of some of the limitations that are associated with graphic pipeline. Because our bottleneck is that graphic pipeline, and how we're going to be able to process those images. So OpenGL and Objects that appear. So OpenGL lacks the object orientation. Actually, so does VRML. There's no object orientation. So consider, for example, a green sphere. So the sphere can be modeled with polygons or OpenGL quadriceps. So actually modeled, and when you say OpenGL, VRML is written on top of OpenGL. It's usually using the same technique in terms of the outside. It's a just different way of programming the same thing with a little bit more automation, actually. So its color is determined by OpenGL state, and it's not a property of the object. It's the state of the color that's changed. It's not really on the object, which means there's no relationship and there's no object orientation. The object isn't green, it's just painted green from its state. Which is kind of interesting because the objects in the real world and pictures that we take in still static, non-dynamic graphics has a state, has an orientation. The picture of the person who's its back, or it's a side view, and it's colored a certain way and oriented. It doesn't change, which is different in modeling graphics. So it defies the notion of the physical object. We actually have no notion of a physical object, so we're creating it by applying the properties to the states. So better objects can be attempted in code using object-oriented programming languages and techniques that are bringing in real images to get real objects. And here's an example of an imperative programming model. Imperative is a type of programming language like C, C++, Java. Well, Java is really object-oriented, but C programming is an imperative language. So this example is a rotate a cube. So we have the application, we have the cube data, and we have the results from running a function, a GLRotate. So the function, the rotation function, must know the cube is represented. Has to have the vertex list, has to have the edge list, and it uses that to rotate it. Which is interesting because there's no concept of the object actually existing. It's just using a method to calculate on a matrix to transform it. So, in an object-oriented model, using an object-oriented programming language like Java as an example, the model is represented and stored in terms of an object. So we have an application with a message to create a cube object, and I rotate a cube object or do something else. So the application sends a message to the object, and the object contains a function or a method which allows it to transform itself, which is different than objects in the real world, because the objects in the real world don't normally communicate with each other. As in a classic example, take those 4 chairs sitting there. They're not all going to rotate together. Actually, if they had brains, and if they could move on their own, they're probably not all going to move together. Instead, humans manipulate those objects, and they change them, which is more of computer graphics oriented, which is what you're doing. So you're taking objects, representing them in terms of objects in the graphics program, and then you're manually moving them. So you're giving them a false object identity. You're giving them, not a true real-world object exposure. So C and C++, in terms of how it's applied, we have a C structure or structure that can be used to build the objects, just the same way as we have a shape that we can create in VRML using a different syntax. C++ provides better support. We can use a class construct, and basically I'm giving you a sales pitch for why you want to use C or C++ versus a higher level language to do this in. You have more control, long story short. So you can use a class construct. You can hide the implementation using the public or private or protected members of that class. And you can also use friend designated to allow classes to access each other. And you can have more interaction with the objects and create more object-oriented behaviors. So if we were looking at a cube object as an example, suppose a simple cube object is to be created and can be scaled, oriented, or positioned. Have this color set directly from the cube, such as cube, my cube. And we're going to set the cube color is going to be equal to something, the cube cover, change the cube color, create a cube matrix that might be associated with it. We can do it from a programming perspective to dissect out all the different methods that we might apply to the object that we're working with. So we have cube object functions to consider. So the functions that act on the cube are required, such as a translate, a rotate, a set color, which is what you're familiar with for the most part for VRML as well. It's using the same base model. So the way of displaying the cube is also needed, so mycube.render or something. So a lot of people have hard-coded this and have created these graphics processing systems to have the user of the program create a cube. And so this is the underlying implementation actually of VRML. So when you create the shape, and the shape is a cube or a cone or something, you're creating it underneath the hood. In the implementation, the library is actually performing creating an object and setting the attributes on the object and translating the object. So we have a public, a private, you know, in terms of the implementation. We have our data members and our member functions that might be associated with it. So for the implementation, we can use the implementation of the private parts, such as the vertex list or something. Whatever data that we're storing about the object itself can be used. And I can access the public members, and don't worry about the public, private, protected. This is just access modifiers and access permissions for certain components of the object. And if you're not familiar with object-oriented programming, it's not going to make any sense to you. But if you are, it might fill in some pieces. So we have the access to the public members, maybe implementation of the class methods that can be used for the implementation without making it visible. So we can render the method. So rendering the method is difficult, but it will be invoked by a standard OpenGL drawing function, such as a GL vertex, which is a standard function. So we also have other objects. The other objects have geometric aspects to them, cameras, light sources. Light sources and cameras we've actually looked at already. So we can add an object to the scene, have the object interact with the other objects. So one object, the light source, provides a light ray on another object, which in turn provides another light ray on yet another object of some nature. But non-geometric objects are also needed, such as materials, colors, transformations, or matrix, which gives us animation. So I'm actually going to be talking more about the transformations next week. Actually, we're going to hit the animations, so it'll make more sense to you at that point as well. Our application code might look something like this. We have an instance of an object cube called myCube, and we have material plastic. My_cube.set material to plastic. So we're creating two different objects. One object is the material property. The other object is actually the cube itself. We're saying, you know, on this object here, set your material property to plastic. And maybe we have another material property called metal. We can set a metal cube, a plastic cube. So we're applying methods to other methods, or sending objects methods and messages, and we're communicating back and forth. I have a camera called a front view. Front view, position the front view camera. So think of it sort of like the real world, where you add objects to a world scene or a graphic kind of environment, which is what you're doing in terms of creating that graphic object. In terms of the light object, we might use one of the lighting models that I went over. And in terms of the lighting model, we can go through and change the perspective to ortho or perspective and stuff. And one of the things I'm going to do for you on December 5th, when we have the final exam review, is go through each one of the topics to tell you what you're supposed to know. Because you may have realized already, I've covered a lot of different topics. Lighting, I was just looking at this going, yeah, ortho and perspective. I actually covered that, but who's going to know that? Who's going to know which one of those two is associated with? And how's that going to work with views? And how's the lighting model? And what's the prong model? You know, you may have seen it already. The word might actually look a little familiar to you. Maybe not. But you're probably going to be at one point, we're going to go, what do I need to know for this final exam? And the final exam will be multiple choice, by the way, so, or multiple guess, I call it. So you won't have to regurgitate exact words, and I'm going to make it so it's doable. It's not going to be extremely technical. And I'll give you, I'm writing it this weekend actually, so I'll be able to give you, hopefully by the 5th, a good understanding of what it is you probably want to review. And all of it will come out of the lecture notes. So I'll even tell you which lecture notes to look at. So, and there'll be some simple questions on VRML and the assignments as well, just to see that you actually did the assignments or went through some of the process. But more details on that later. But I kind of looked at this and went, I wonder if they remember we went over this stuff. Probably not. Who knows? Maybe you do. I mean, at one point, eventually some of the vocabulary is going to look familiar to you. Like, I would hope you probably know what a rotation is, or a transformation is, and how they're different maybe. Hopefully you're familiar with the XYZ axis and origin at this point. And view perspectives, and the viewpoint, and the camera angle, or the camera, what's considered the camera perspective. Maybe the lighting models are kind of fuzzy, but maybe, you know, the differences between a pinpoint light, maybe. Because some of it's stuff you're familiar with from other classes, or from computer graphics in other forms, like camera or film or something. So in terms of the scene descriptions, going back to this concept in the future figure model itself, the model can be described either by a tree or by equivalent code, as we've seen before. So do we know that hierarchies of models or objects are in a tree? They have nodes in them, hopefully, or something equivalent to it. Or we have a generic traversal that can be applied, that can be written to display it. It's kind of like a preorder traversal that I talked about, so we can know that the legs always move. The person walks by moving their foot first, and then their ankle, and then their thigh, and then the torso moves with it. You know, if the torso moved first and the leg moved last, then we would get some interesting movements that, you know, in fact, that's how people be funny, you know. Let's move funny. You know, so these people move their torso first and their legs second. That's what I meant by preorder traversal through the tree, the hierarchy of the object or the humanoid in terms of which matrix C you're going to translate first. And the translation is moving from one position to another. Rotation is generally referred to as a left or a right, kind of a constant circling or movement around an axis. So rotation is generally associated with axes. And whether it be the x, y, or the z axis, you're going to circularly rotate coordinate systems around the center points. And a translation, as we remember, is to go from one position to another, to translate to move in the plane. So it's a movement. So animation, we look at both of those actually, rotation and transformation. So if all of the elements in the scene or the camera, the light, the model, geometry can be represented as C++ objects, then it can be shown as a tree. So then we can render the scene by traversing this tree. When we render the scene, we have our coordination system. So just like we saw the humanoid, each individual object might be composed of several other objects, and there might be a tree created for each one of them. We also might have a main scene. As an example, the scene of this classroom. We have students, and the students are oriented with the desks. They're sitting in the desks, and the desks are on the carpet. Scene has a carpet, scene has a wall. I see some pictures on the wall. I see some light above me on the ceiling, some sprinkler system. And all that stuff is part of the hierarchy. And we know we've painted the scene correctly when we've oriented the realism. So if this were a computer program that we're in right now, if we put the chairs on the, instead of putting them on the floor, we actually had them rotated in the position of them sitting on the ceiling. Most people would look at that scene and go, there's something wrong. Why are the chairs sitting on the ceiling? And we don't really think about that in the real world because we don't have to, but we're building this in a computer program. So we have to do what's called the scene graph. The scene graph would put the chairs on the floor instead of turning it around and putting the chair on the ceiling. So we define the graph of the scene by the orientation of the objects, the positioning of the objects, the rotation of the objects, which gives us our desired scene, our room. So scenes, sometimes referred to as worlds. Usually we have a scene inside of a world. So the hierarchy, the biggest component is the world. Inside of the world we have our scenes. This might be a scene in here. There's a scene outside in that hallway, actually. There's a scene in the room next door to us. These are sub-scenes or sub-components of the world. And we can go on forever with that one because the entire world is composed of many different scenes. So here we can isolate out, and we have separators here in this particular scene where we can isolate the state of the sub-tree beginning at a separator node from the rest of the tree and say that this one here from our scene we have the color, the translation, the rotation, the object, one that's going to translate with object number 2. And then we have another separator over here where we can dissect out a separate object number 3 that has a separate rotation, a separate translation to it, which is kind of interesting. In fact, we have humans, which have a separate rotation and translation with desks. Desks don't really do very much. They're going to move differently. Desks won't get up and walk. So desks don't normally move. They're more stationary, usually, in the classroom. So. But the humans aren't. And the floor never moves. There's no translation, there's no rotation on the floor. The ceiling's about the same thing. We can apply a lighting model to the ceiling. And we can turn on and off the lighting model, so the states might change. So we might want to keep that as a separate, create a separate separator for that. But if I were to take this room out, I have like 1, 2, 3, 4 separators probably. One for the ceiling. The ceiling is actually kind of complex, actually, because we have a lot of shading models going on with that. The floor is pretty simple. And if I were to dissect out the walls, I could have a separator for that as well if I wanted to. And some walls have pictures on them. Some walls have more pictures than others. So back wall doesn't, half the wall doesn't have a picture on it. So going back to the preorder traversal, we have the states, so we can preset, and will save us computational time. We know the chairs probably aren't going to move. So if the chair does move, or if the human moves, we have a preorder traversal. So humans are going to walk in the room, and they're going to sit down in a chair. They're going to get up from a chair, they're going to walk out of the room. So we can set that movement and the traversal through the scene, and we can predetermine what's going to happen. So I think looking into a crystal ball in your computer graphics program, you can actually tell what's going to happen in the scene. So, which is how you would think if you're going to essentially assemble an OpenGL video game. So you know what's going to happen, hopefully, from the actions of the characters. Those are going to be objects that are going to be in the scene. You have one scene that's going to lead to another scene. You can break the scene out into separators, and each one of the scenes can have different effects that are associated with it. One room might be dark, another room might be lit. You might have different characters in each one of the rooms if you're doing some sort of a simulation or fantasy game or something. Depends on the nature of the game. And in terms of your computer graphic components, you're essentially creating the objects needed to simulate the environment that you're playing the game in. And which is kind of interesting because nowadays the games have much more sophisticated scenes than they used to, like water that actually moves instead of just being water, or chairs that fold, or chairs that do something that are different than just a chair. So primitive have objects that don't move, objects that just sit in a position and you walk through, which is, for game experiences, not so realistic these days. So here's a preorder traversal where we're going to come up with a way of translating and ordering how the objects are going to be oriented and moved and positioned. In the separator node, as I mentioned before, it's necessary to isolate the states out. So it's equivalent to the OpenGL pop and push. And we have a separator where this is ending and that's starting, and now we're going to traverse through a different object. And the separators are usually by object groups. As an example, that chair is not going to be one object. It's going to be like 1, 2, 3, 4, 5, maybe 5 or 6 different sub-objects that are going to be in a hierarchy to create that chair, which is kind of interesting. And you really see that when you start putting together objects using VRML or using OpenGL, or any graphics library actually for that matter. When you start building it, you never really thought about how many objects are there. I don't know how many bones there are. Somebody could tell me how many bones there are in the human body, but that's a great hierarchy right there, the skeletal system. I think we got tons of bones. So I don't know exactly how many. I guess I should know, but I don't know how many bones there are. Over 100 at least, I think. So, and people, I don't know, chiropractors, I think, memorize all that stuff so they know which bone's connected to which bone. Hip bone's connected to the arm bone. Not really. But so that they can traverse through, pre-traversal through to know which is going to lead to which, so that they can adjust the system for chiropractic kind of care and stuff. So doctors certainly have a good memorization of all the bones in the system. But that's a separator. That's knowing that the bones are connected somehow, and that the human is separate from a dog, that's separate from a car that the human is sitting in. But if you have the model separated out properly, you can put things in correct orientation and not confuse something. So, which is kind of interesting when you think about how stuff is rendered. So as with the figure model, the same approach is used. The universal traversal algorithm can be written, and so the order of the traversal can matter. So if the scene node is not used, the state changes can propagate. So the scene does matter. If, for example, you're painting a scene of a beach and it comes out dark first, probably going to make it light first and then go darker. Because, in fact, you see this as an effect, visual effect. If you're going to open up a scene and it's supposed to be dark, you're going to start out dark. If it's supposed to be light, you know, beautiful sunny day, it's going to be light and then go darker. Hopefully because you're going to create more realism in terms of the traversal through the scene. If you're going to do this in computer graphics, you're going to think about, well, how do I make it look realistic? So then you have to go back to physical properties of the environment and go, well, does the room normally start out dark or does it start out lit? Or if it's starting out light, you might want to make it gradually darker. When we enter into rooms, usually when we enter into rooms in computer graphics, it's always black. And then we start painting things because we're not going to paint it unless we need it. And if we see something in the lights, it's a better visual effect. If it started out where you could see everything, it makes no point of entry, for an animation point of view, it doesn't make any sense because we never really, if it's nighttime, we never really walk into a room that's well lit. So, but it's something that you can think about in terms of the scene and the traversal of the objects. So we have a couple of different programs. We have Inventor and we have Java 3D, which are another packages that we haven't looked at yet, but probably not going to. These are more advanced packages than VRML. But Inventor and Java 3D provide scene graphic APIs. So a lot of your higher-end programs are going to give you scene graphics, where you're adding objects, and the OpenGL component of it is used to create the objects. And then you put the objects in the scene graphics and use the scene graphic APIs for it. So scene graphics can also be described by a file or a text or a binary file. Implementation is independent of the way they're transporting the scene, and supported by scene graphic APIs usually. So however primitive supported should match the capabilities of the graphics system. So hence most scene graphic APIs are built on top of OpenGL or DirectX for PCs. DirectX, I believe, is only available on PCs, and it's not available on the Mac systems, but OpenGL is more cross-platform compatible. And then lo and behold, we have the graphic package that we've been using in this class, hopefully. You've been using it because you have some assignments due in a couple weeks. It's called VRML if this is your first exposure to it. So scene graphics can be used over the World Wide Web, and this is a scene graphic animator. So you need links to other sites to support distributed databases and distributed objects themselves. You can actually connect. In fact, one of the tutorials I gave you earlier on in the course actually connected using a URL. So you clicked on something and it brought you to another website, which you can do inside of which is really nice because you have that connectivity inside of the scene that you're creating. So virtual reality markup language is what VRML stands for. It's based on an Inventor database. So it's based on an Inventor database. It's implemented with OpenGL. So all of the OpenGL stuff that I'm giving you is relevant because it's the underlying implementation of VRML. So it's superseded by X3D and ISO standard for real-time 3D graphics. So it's the base, and then we have other packages that are on top of that. I'll run with it. So I'm going to stop this video and start another kind of a short one. So let me stop this one.